All right, this is lesson 6, theorems about roots of polynomial equations. Our essential question is, how are the roots of a polynomial equation related to the coefficients and degree of the polynomial? Okay, here's our table of contents. The rational root theorem. So the rational root theorem states, let P of x equals a sub n x to the nth plus a sub n minus 1 x to the nth plus a sub 1 x plus a sub 0 be a polynomial with integer coefficients. Okay, so basically this is any polynomial. If the polynomial equation P of x equals 0 has any rational roots, so again, a rational number is a number we can write as a fraction, then each rational root is of the form P over Q, where P is a factor of the constant term, a sub 0, and Q is a factor of the leading coefficient, a sub n. Okay, so basically, if it has a rational root, so if it has a number that can be written as a fraction, where it will cross the x-axis, I can write that in terms of a sub 0 and its factors divided by a sub n and its factors. Identify possible rational solutions. So example, from the graph, it appears that negative 8 is the zero of the function 4x to the fourth plus 13x cubed minus 124x squared plus 212x minus 8. Without substituting, how can you determine if 8 is a possible solution to P of x equals 0? Okay. So based off of this information and looking at it, it looks like negative 8, which is right here, okay, is a possible 0 for this equation. Okay. If that's the case, I want to use what I know about rational roots. So I'm going to look at negative 8 and I'm going to look at 4. Determine the constant term and its factors. So again, the constant term is the number without any variables attached to it. So in this case, our constant term is negative 8. Our factors of negative 8 are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. So these are all numbers that divide in evenly to 8, right? Or they're multiply factors to get me 8. Because 1 times 8 would give me 8. 2 times 4 would also give me 8. I determine my leading coefficient and its factors. In this case, my leading coefficient is 4. Again, our leading coefficient is the number in front of the variable with the largest exponent value or the largest degree, okay? So our leading coefficient is 4. Its factors are plus or minus 1, plus or minus 2, and plus or minus 4. You always have to include this plus and minus sign because any combination of these is what's going to give us that leading coefficient. Okay. The rational root theorem states that the possible rational roots of P of x equals 0 are all of my values, my factors of my constant term, divided by all the factors of my leading coefficients terms, okay? There may be some that overlap. So like 1 over 1 is 1. 2 over 2 simplifies to 1. 4 over 4 simplifies to 1, okay? So you're doing all of the combinations thereof. Therefore, I always like to stick with the factor for the constant term on top and then write each of the factors underneath on the denominator for the leading coefficient. So like 1 over 1, 1 over 2, 1 over 4. And then I go to my next factor for my constant and I repeat the factors below. So 2 over 1, 2 over 2, 2 over 4. 4 over 1, 4 over 2, 4 over 4, 8 over 1, 8 over 2, 8 over 4. You can notice that a lot of these are going to be a repetitive pattern, and you won't need to write all of them if you've already got them considered in your rational root theorem factors, right? So realistically, 1 over 1 is 1. I have 1/2, 1/4. 2 over 1 is 2. 2 over 2 is 1. I already have that, so I wouldn't need to actually write it again. 2/4 simplifies to 1/2, so I wouldn't actually need to write it again. 4 over 1 is a new one. 4 over 2 is 2, so I wouldn't need to write that. 4 over 4 is 1. 8 over 1 is 8. I don't have that. 8 over 2 is 4. Have that one. And 8 over 4 is 2. So really, I would just need to write these 4, this one, and this one to be possible solutions for this equation. So in this case, we do have 8 over 1. So, and plus or minus 8 over 1. So if 8 was negative and 1 was positive, we would have a potential 0. Use the rational root theorem. So a storage company is designing a new storage unit based on the dimensions shown. You have a width of x, a length of x minus 2, and a height of 2x minus 3. The volume of the container is modeled by the polynomial v of x equals 2x cubed minus 7x squared plus 6x, where x is the width in feet. What are the dimensions of the container in feet if the volume of the unit is 154 feet cubed? Okay. So we got the 2x cubed minus 7x squared plus 6x by multiplying. For volume, it's length times width times height. So x times x minus 2 times x minus 3 gives us this polynomial. The volume is 154 cubic feet. They told us that in the problem. So we can find the solutions to the equation by setting the polynomial that we have to find our volume equal to whatever our volume needs to be, in this case, 154. I'm going to move 154 to the left side of my equation. So I'm going to have a polynomial function of 2x cubed minus 7x squared plus 7x minus 154. Okay. I'm going to identify my constant term, negative 154, and my coefficient, my leading coefficient, which is 2. So I'm going to got my constant term, which is negative 154. Here are my factors. Leading coefficient is 2 and my factors. Okay. So now I can list out all possible rational roots, eliminating repeated values. So this time I did eliminate some of the repeated values, but not all of the repeated values. So like 2 over 1 is 2, 2 over 2 is 1. So I can get rid of that one. 22 over 2 is 11, so I can get rid of that one. Right, so I got rid of this one. I got rid of this one. Okay, 154 over 2 is 77, so that one goes away too. Okay, so these are the values that I'm left with. I'm going to look for a value where 2x cubed minus 7x squared plus 6x minus 154 equals 0. And I can test these numbers. So I can put 1 in, so 1 cubed times 2 minus 7 times 1 squared plus 6 times 1 minus 154. Okay, by substituting values in, I find that 11 halves, or 5.5, is a solution. Okay, so if I substituted it in, I got 0 in the end. So I'm going to use synthetic division to find the other factor. So I did 11 halves. I'm using synthetic division, so I brought down my 2. 2 times 11 halves is 11. Negative 7 plus 11 is 4. 4 times 11 halves is 22. 6 plus 22 is 28. Negative 28 times 11 halves is 154. Negative 154 plus 154 is 0. So I have x minus 11 halves times 2x squared plus 4x plus 28. The next thing that I can do is figure out what my discriminant is. So can I solve anything? I can take a 2 out of here. So I'd have x squared plus 2x plus 14. That's still not going to give me, if I try to factor it, it's not going to work. So I'm going to find the discriminant to determine if the quadratic equation can be factored further. The discriminant, remember, is what the value was underneath the radical sign. So in this case, the square root of b squared minus 4ac. that b squared minus 4ac, that's my discriminant. So b squared minus 4ac, I have a b of 4, an a of 2, and a c of 28. I substitute those values in. 4 squared minus 4 times 2 times 28 gives me 16 minus 224, which is negative 208. Okay. Since the discriminant is negative 208, it's a negative number, I'm not going to have any other real solutions or real zeros. So there's no other place where this cubic function crosses the x-axis. So therefore, 11 halves is the only real solution to the original equation. So I'm going to substitute that 11 halves in for my width, my length, and my height to figure out what are the possible dimensions for the container in feet. Okay. So width is 11 halves or 5.5 feet. My length is 11 halves minus 2 or 3.5 feet. My height is 2x minus 3, which ends up being 8 feet. Okay, so the dimensions are 5.5 feet, 3.5 feet for length, and 8 feet for height. Fundamental theorem of algebra. The fundamental theorem of algebra states that p of x is a polynomial of degree n is greater than or equal to 1, then p of x equals 0 has exactly n solutions in the set of complex numbers. If p of x has any factor of multiplicity m, I count the solution associated with that factor m times. So for example, the equation x minus 3 to the 4th equals 0 has 4 solutions. Each of them are equal to 3. So basically what this says, whatever my highest degree is, whatever the degree of my polynomial is, that's how many factors I will have. So if I have a binomial or an x raised to the second power, I will only have 2 solutions. Now, those 2 solutions could be real solutions, they could be complex solutions, they could be imaginary solutions, but I will have that many solutions for that problem. Find all complex roots. So what are the complex roots of the polynomial equation 3x to the 4th plus 4x cubed plus 2x squared minus x minus 2 equals 0? So I know just by looking at this equation, the degree of my polynomial is 4. I'm going to have 4 roots. Now, whether they are real or imaginary or complex, we don't know yet. But we know that there will be 4 when we are done. Okay. So the first thing I want to do is I want to recognize that 3 is my leading coefficient and negative 2 is my constant. So I can figure out what possible solutions I would have. My factors for negative 2 are 1 and 2, and my factors for 3 are 1 and 3. So now I can list out all my possible solutions. So 1 over 1, 1 over 3, 2 over 1, 2 over 3. In this case, I don't have any that repeat. I don't have any that are like terms. So these are the 4 possible solutions that I have. I'm going to test by substituting values in. I'm going to find that 2/3 does give me 0. So 2/3 is one of my roots. And negative 1 is also one of my roots. Okay. So I'm going to use synthetic division to factor the 0 of 2/3 out. And then I'm going to use synthetic division to factor out the negative 1 out. I'm going to use the quadratic formula to find the last 2 roots. So x squared plus x plus 1 does not factor easily. So I'm going to use negative b plus or minus the square root b squared minus 4ac all over 2a, where my a is 1, my b is 1, and my c is 1. I also factored out a 3 here just to make my life a little bit easier. You can leave the 3 in. You can leave it as 3 squared plus 3x plus 3. You'll get the same answer. So when I utilize the quadratic formula, I get negative 1 plus or minus I square root of negative 3 over 2. So my complex numbers, this negative square root of 3 over 2. So the complex numbers, 2/3, negative 1 minus I square root of 3 divided by 2, and negative 1 plus I square root of 3 divided by 2 are the 4 roots of this equation. Okay. So again, since the polynomial has a degree of 4, the fundamental theorem of algebra states that these are the only 4 roots of the equation. I can't have any other ones. Irrational roots and coefficients of a polynomial. How are the types of zeros of a polynomial function related to the coefficients of the polynomial? Suppose a quadratic polynomial function p has one rational zero c and one irrational zero a plus the square root of b, where a and b are rational numbers. Are all the coefficients of p rational? Okay. So basically I can just write this out. So x minus c, that's my rational zero. So that's my whole number or fraction. Regardless, it's something that I can rewrite as a fraction. And then I have one that's irrational. So that's square root of something. So like square root of 3 would be an irrational number. It's not a number I can write as a decimal without repeating. It's a non-repeating decimal, or it's a number I can't write as a fraction. So I'm going to go ahead and multiply this through. So x, this negative sign I distributed, so I get x minus a minus square root of b. And then I times x minus c, so x times x gives me x squared. X times a is negative ax. X times square root of b gives me the x square root of b. C times x, c times a, and c times square root of b. I can also factor out an x in this first 3, ax minus x times square root of b minus c, and the second one. So no, the function p has 2 irrational coefficients, so it does not all the coefficients in this case are rational numbers. Okay, I have 2 irrational numbers. Okay, suppose a quadratic polynomial function r has 2 irrational zeros, a conjugate pair a plus square root of b and a minus square root of b, where a and b are rational numbers. Are all the coefficients of r rational? So in this case, yes, all of the coefficients are rational. If I have a conjugate pair, right, a plus square root of b times a minus square root of b gives me a squared minus the square root of b squared, which is just b. Okay, so you can notice that all of my factors are going to end up being rational coefficients. How are the types of zeros of a polynomial function related to the coefficients of the polynomial? So a quadratic function with one rational zero and one irrational zero will have some irrational coefficients. They won't necessarily all be irrational, but they'll have at least one irrational coefficient. Okay. A quadratic equation with a conjugate pair of irrational zeros, so a plus square root of b or a minus the square root of b, will have only rational coefficients. So as long as there is a conjugate pair, I will only have rational coefficients. Conjugate root theorem. The conjugate root theorem states let p be a polynomial function with rational coefficients and let a and b be real numbers. Then if a plus square root of b is a root of p of x equals 0, then a minus the square root of b is also a root of p of x equals 0. If you let p be a polynomial function with real coefficients and let a and b be real numbers, then if a plus bi is a root of p of x equals 0, then a minus bi is also a root of p of x equals 0. So basically what it's saying is if you have its complex conjugate for non-real roots, its complex conjugate will also be a root of 0. Write polynomial functions using conjugates. What is a quadratic function p with rational coefficients in standard form such that p of x equals 0 has 2 plus 5i as a root? So since it has 2 plus 5i as a root, its complex conjugate will also be a root. Okay, so 2 plus 5i and 2 minus 5i. Since I know, right, that this is a quadratic function, meaning x squared or x to the second power, okay, I will only have 2 roots in this case. So 2 plus 5i and 2 minus 5i are my roots. So I do x minus the 2 plus 5i and x minus 2 minus the 5i. And then I'm going to distribute the negative signs. and then I'm going to multiply it through. So I'm going to get x squared minus 4x plus 4 minus negative 25, which turns into plus 25. 4 plus 25 is 29. So x squared minus 4x plus 29 is a quadratic equation with 2 plus 5i as a root. So a polynomial function q of degree 4 with rational coefficients has zeros 3 minus square root of 7 and 4i. Again, I'm going to use its complex conjugates. So I have 3 minus square root of 7 and 3 plus the square root of 7 and 4i and negative 4i. I multiply all four factors together. So again, x minus 3 minus square root of 7, x minus 3 plus the square root of 7, x minus 4i, and x minus negative 4i. So I get the values of x to the fourth minus 6x cubed plus 18x squared minus 96x plus 32 once I multiply everything out. Summary. So in conclusion, we have a couple different theorems. We've got the rational root theorem. Okay, so basically says all my factors of my constants divided by all the factors of my leading coefficient will give me all of my possible roots for that polynomial function. The fundamental theorem of algebra states that the highest degree of a polynomial, that's how many complex solutions that I could have. Okay, I can have exactly that many solutions. My conjugate root theorem basically states that if I have a square root or an imaginary number, I can use the complex conjugate. They have to be included because they're also roots of that polynomial. And that is the end of lesson 6.